Welcome to the afternoon session, and we have two talks, first of which will be Catherine Greenhill, who will be talking about asymptotic enumeration contingency tables.
Excellent. Thank you, Martin. So I don't do as much Markov chain stuff as I used to, but if you look at the description of this web page, it says MC approaches and alternatives. So this falls under alternatives. I do a bit of asymptotic enumeration these days, which I blame Brendan McKay fully for. So this is joint work with Brendan. I'll talk about asymptotic enumeration of contingency tables. As many of you know, a contingency table is just a matrix with specified row and column sums that you want to fill in with non-negative integer entries. And they're very important in statistics, and because of this there's been a lot of interest in algorithms for approximately counting them and also for almost uniform sampling. In this talk I'm going to focus on counting because it's the closest to enumeration. Okay, so if you're counting them, you'd want to know how many ways can I fill in the matrix with non-negative integers to give me my specified row and column sums. And when you're talking about algorithms, your goal is a fully polynomial randomized approximation scheme, which Eric defined this morning. So this has to be an efficient algorithm, polynomial in the size of the table and the logarithm of the table sum. And it also has this user-defined tolerance, epsilon, on the relative error. So that'll be important in what I say. Now, there's been various results from this community on algorithms for approximately counting contingency tables. Some Markov chain approaches that culminated in the Markov chain of Cryan, Dyer, Goldberg, Jerem and Martin for a constant number of rows. Also for a constant number of rows, Mary, who's just sitting down, and Martin did a combination of volume estimation and dynamic programming. And then after that, Martin showed us how to do it with dynamic programming, and that was the most efficient algorithm there for a constant number of rows. Can everyone hear me? All right? Yeah, okay. In another sort of regime, when the tables are dense, by which I mean all the row and column sums are sufficiently large, you can reduce to volume estimation, as was shown by Dyer, Cannon and Mount in 1997, and then this was extended by Morris, who showed that it would still work if you lower that lower bound on the size of the row and column sums. So that's a sort of summary of the algorithmic results if you want to approximately count. But a related problem is that of asymptotic enumeration. Instead of an algorithm to produce an estimate of your number, you want a nice formula that is going to give you something very close to the number you're trying to get, with a relative error which tends to zero as m and n tend to infinity. So that's the goal in asymptotic enumeration. And the number that we wish to, there we go. The thing we're trying to approximate is the number of contingency tables with the given row and column sums. I'll denote that by m of vector s vector t. Okay, so we are looking for just a nice formula with a small error. And our formula will depend on some parameters here. The maximum row sum is little s, the maximum column sum is little t, and capital S for some reason is the table sum. So there's too many s's in this talk, I apologise. The capital S is the sum of all the entries in the whole table. Okay, a bit of history of the enumeration problem. You can think about these contingency tables, it's actually the same as a bipartite multigraph, right? And Reed in 1958 in his PhD thesis looked at enumerating a lot of different types of cubic graphs, cubic bipartite graphs and cubic bipartite multigraphs. And this gives you asymptotics of contingency tables where all the row and column sums are equal to 3. That's a specific case of what we call a semi-regular problem, where all the row sums are the same and all the column sums are the same to each other but might be different from your row sums. And we write that using a slightly different notation, as you can see here. So Reed got the ball rolling in 1958, and then 3 independent groups of people in the 70s looked at constant row and column sums, and that's Everett and Stein, Bekesi and Comlot and Bender. And now you want to enable S and T to tend to infinity as M and N do, and you still want good asymptotics. Really the only thing on this so far was Canfield and McKay, who proved an asymptotic formula in the sort of dense case when all the row and column sums are sufficiently large. Now, and there are a few other things, the matrix had to be sufficient, close to square and blah blah. There are some technical things that have to hold. In the dense regime, you're not using combinatorial methods. You write M of S, vector S and vector T or whatever as a coefficient in a big generating function. You want to extract that coefficient using Cauchy's coefficient formula, and you're evaluating a multidimensional contour integral where the number of dimensions is tending to infinity because it depends on M and N. So you're doing lots of complex analysis, and that's not what I'm going to be talking to you about today, which makes me happy. And maybe it'll make you happy, but that's analytic methods because it's the dense case. But they also actually generated some data and tried to make a conjecture about how this quantity behaves. And they conjecture this not only in the dense regime that they were looking at, but actually that whatever the vectors of row and column sums are, they conjectured it could be written in a certain form, which I'm not telling you, I apologise, but where the error, it's not a big O, it's like a constant which is between 0 and 2. So rather than putting a big O, they're putting quite specific bounds on the form of their error, which unfortunately, I apologise, I'm not showing you. And this conjecture has been proved in a few cases. If the matrices are square and small, then there are some exact values given by Beck and Pixton, and they verify the conjecture holds. And also Brendan and Rod did lots of simulations and verified it for several thousand values of the input parameters. Now what Brendan and I did, the result I want to tell you about today, verifies the conjecture in a certain sparse regime where the product of the max row sum and the max column sum grows slower than m times n all to the 1/5. So that's a sparse matrix. Most of the entries would be 0. But actually the expression we got holds more generally. It doesn't always verify the conjecture more generally. It holds more generally, and it holds in the irregular case. All the S's don't have to be the same and so on. Our condition is that the product of S and T grows slower than the table sum to the 2/3. So that's as far as we can push this. All right. I'll tell you our result, at least in one of the nice case of it. We need a couple of parameters I'll call mu and nu, which are, the exact definition is they're sort of scaled central moments. So they're measuring how much the row sums vary and how much the column sums vary. We assume that M and N tend to infinity, the table sum tends to infinity in such a way that our condition holds S times T grows slower than capital S to the 2/3. Now, we get an expression in that case, no matter what, but if in addition mu and nu and the product of mu times nu are all small enough, order of S to the 1/3, then the asymptotic expression we get can be written down like this. And I'm claiming this is a nice formula, and I'm going to tell you on the next slide why it is a nice formula. So it's got these binomial coefficients, and then it's got the extra factor which is within an exponential.
Sorry, if mu and nu were 0, sort of ideally,
right.
Whatever.
This is just eta 1/2 plus error. It just all goes away. Yeah, and in many cases when the row and column sums are sufficiently small, then mu and nu are going to be so close to 0 that you can stick the rest of it in the error. So you can think of it as e to the 1/2 plus O of 1, I mean little o1, if you like, but it does hold a bit more generally. Now if this
you get a slide back, you claimed a better result for the semi-regular case than for the general case, right? There was a better error term.
Is it better? Oh, it's just it verifies McKay and Canfield's conjecture. It just can be rewritten in the form that fits in with their conjecture.
Oh, I see.
Yeah,
it's different.
It's different to this. But if you don't have this condition in red, but you still have our overriding condition that s times t is little o of table sum to the 2/3, then you get a similar expression to this, but with a lot more terms. It's just a bit uglier and I left it off. But you get the same order of the error term. This is my favourite little o one here, s times t times capital S to the 2/3. Okay, so why is this a nice formula? It's got this nice interpretation. We can write the number of contingency tables in our set as m times p1 times p2 times e. M is the number of compositions of the table sum capital S into mn parts. So it's the number of ways you can fill in the contingency table so that it's got the correct overall table sum. It obviously won't always have the right row and column sums. And then you can think of the uniform probability space on that set of all contingency tables with the right table sum. And P1 will be the probability that all the row sums are correct, right? Because the ith row sum, that's just the number of ways to fill it in to get it right. P2 is the probability that all the column sums are correct, and a first year might tell you, therefore, m of st is m times p1 times p2. But of course, that's not the case because these events are not independent. But it's nearly true in the sense that all we have to do to fix it is multiply by this factor e, capital E, which, as we've said before, when mu and nu are quite small, this is basically e to the 1/2 plus some little o1. So that's kind of nice. And what's interesting is, in the case, just as contingency tables correspond to bipartite multigraphs, if you're looking at 0, 1 matrices with the given row and column sums, you've got bipartite graphs. And we did an asymptotic formula for those. You get exactly the same setup with an e to the minus 1/2 in there instead of e to the positive 1/2. So that's quite nice.
Is it sort of easy to see intuitively whether e should be bigger than 1 or smaller than 1?
No, not really. Not for us anyway, no. And yeah, sort of you think of negative correlation and positive correlation, but why should e be greater than 1 is a bit strange. But yeah, it just came out, I suppose. But anyway, we like it, and so that's why I claim it's a nice formula. Okay, so what I want to do is tell you a bit about how we proved this, and then pose a different question at the end. It turned out, to get this result, we had to prove 3 key facts. So we think of calligraphic M as being the set of all the contingency tables we're trying to count, the ones with the correct row and column sums. We have to prove that with high enough probability, which is with 1 minus this, little s, little t cubed divided by s squared, which is little o1 under our assumptions, a randomly chosen contingency table with the correct row and column sums has no entry 4 or greater. You just don't see them. You've only got 0s, 1s, 2s and 3s in this contingency table. There are not many 3s and there are not many 2s. And the definition of not many is technical and I'm not going to show it to you, but it's not too bad. If you have those 3 facts, you know those, we could just completely wholesale pull in a whole lot of calculations that we'd done in the 0-1 case. And you know, saving yourself work is always nice. So that was worthwhile doing. And we're going to prove these key facts using the method of switchings. So switchings is a method, I guess, pioneered by Brendan McKay and used by lots of other people to prove nice combinatorial things. And in the simplest form, it's just double counting. So you have a set on the left, a set on the right, you've got some edges going across them, and you want to compare the sizes of the 2 partite sets in your bipartite graph. If you have a lower bound for the number, a lower bound on the average degree on one side, an upper bound on the average degree on the other side, and you count your edges twice, you do it the right way around, you get an upper bound on the relative sizes of the 2 sets, especially if you write them down in the right order. I always forget which one goes on top, but you think about it and you get this nice bound. And switchings is a sort of generalization of this. And in order to help people perform their switchings argument and analyse it, Brendan and Berlafac have proved a sort of general purpose switchings theorem. This paper appeared in the Australasian Journal of Combinatorics, and this is actually a special case, so what they show is more general than this. But I'd like to tell you about this theorem and then we'll see how to apply it. So you've got the key ingredient is there's a finite simple acyclic directed graph lying underneath all of your switchings. Each vertex in your directed graph corresponds to a set, C of V, and the sets, we're going to be interested in the relative sizes of some of these sets. All of these sets are pairwise disjoint. Calligraphic S is a set of ordered pairs such that if QR is an ordered pair in calligraphic S, then Q belongs to the set C of V, R belongs to some set C of W, and there must be an edge from V to W in the underlying directed graph. Now these pairs Q and R are going to be things that are related by a switching operation. Usually switchings are designed to get rid of defects. So you're taking away a defect from Q to produce this thing R, and there has to be an underlying edge in the directed graph to help you to do that. Also as input, you've got things which are like the lower bounds on the average degree and the upper bound on the average degree that I mentioned earlier. So positive real value, that probably should say positive. They're positive real valued functions on the vertices such that the number of pairs QR where the first component Q belongs to C of V is bounded below by A of V times the size of C of V, and similarly the number of these pairs where the second component belongs to C of V is bounded above by B of V times the size of C of V. This is part of the input to the theorem. You also take a non-empty subset of the vertex set, Y. That's not a question. The set is called Y, sorry, and you're interested in the size of the union over all the vertices in Y of these sets C of V relative to the union over everything. So that Y is also part of your input. And the theorem says if you want to bound this, it suffices just to look at directed paths. You'll have a directed path V1 down to VK in the digraph. V1 starts off in your set of interest Y. VK has to be a sink in the directed graph. And then you've got this upper bound, which looks like this, of the form, I'm not very good with this pointer. You have some other functions, n of V, which are defined in terms of the A's and the B's, as explained below. And you sum, for the numerator, you sum over your directed path, just the vertices in the path that belong to Y. You sum up their values n of Vi, divided by the sum over the entire path n of Vi. The point is, when you want to apply this, you just take a worst case directed path. So it allows you to narrow your focus down onto just directed paths in your directed graph that look like this. And you get a bound. So that's the switchings theorem. The switchings that we're going to apply this to are designed to get rid of large entries in the table. So we'll have something called a D switching. You take a table Q, and I've got equals here, but really the matrix I've shown is just a submatrix that you can find somewhere within the table Q. You might have to permute rows and columns to get it up in the top left or something, but it looks like this. There's an entry equal to D with D zeros in the same row, D zeros in the same column, and down the diagonal, well, it's a diagonal if you put it in the right order, you have entries Q1 down to QD, which cannot equal 0 and they cannot equal D plus 1. And then you do the switching, which turns the top left-hand D into a 0, spread that weight along where all the zeros were before they become 1, subtract 1 down the diagonal, and leave everything else alone. Okay? By our choice of the QI, everything's still non-negative integer. The row and column sums are all fine. You've got rid of at least one D. In fact, you may have got rid of as many as D plus 1 Ds, because some of those QIs could equal D. And the other critical fact for us is that you have not changed the number of entries which are greater than D. That's why QI cannot equal D plus 1. So you'll see later why that's important. So these are the switchings that we perform here. And the reverse operation is a reverse D switching. We have a lemma that gives us those lower bounds and upper bounds A of V and B of V that we need in the theorem. And you need these quantities Sk and Tk, which is just the sum. Sk is the sum over all of the rows of Si falling K, falling factorial, right? So they're just some numbers that you work out. if you take a table in this set, it has at least k positive entries which are less than or equal to d, and k has to be at least 2st for this to work, and it has at least j entries which are exactly equal to d, then you've got at least j times the dth power of k minus 2st d switchings out of q, and at most sd times td ways to do a d switching into q. So that gives us lower and upper bounds that we need for the theorem. And that's not difficult to prove. Okay, so now I'd like to show you how we can apply this lemma to prove something nice. And we're going to just establish our first key fact, that there's not many entries greater than or equal to 4 in these tables. So we let U1 be the set of all matrices in our set of interest which has at least one entry greater than 3. The relative size of this set is our favourite little o1, well, our favourite little o1 cubed, so it's order s cubed t cubed on capital S squared. How we do this is we're going to inductively work backwards from the largest possible entry you could put in this table, which is called delta, which is the minimum of s and t. And let from d equals delta, delta minus 1, and so on down to 4, we'll successively rule out that the maximum entry could be equal to d in very many of these tables. So let's define the set md of j to be all of the matrices in our set with exactly jd's. And j might be 0 and none greater. So everything in mdj has maximum entry at most d, and let md positive be the ones that really do have a d in there. So it's got a positive number of d's. Then the set md plus 1, 0, maximum entry at most d, is equal to the ones which have maximum entry at most d minus 1 plus the ones where you really do have a d in there. And we're going to bound the ratio we're interested in, the number of matrices that really do have a d compared to everything else. You can upper bound that by the number that really do have a d by the number whose greatest entry is less than or equal to d. And we're going to do that using the switching theorem, using our d switching. So we assume we're just looking at matrices that have nothing greater than d in them. And we're going to use the d switching, so our vertex set is v0, v1, v2, so on, where the jth one, vj, corresponds to the set where you've got exactly j entries equal to d, right? When you do a switching, you go from vj down to vi, where I is at most j minus 1, because you definitely get rid of at least one d, and I can be as small as j minus d minus 1, because you might get rid of at most d plus 1 entries equal to d. So that gives the edge set E for our underlying directed graph. Calligraphic S is just simply the set of the matrices, pairs of matrices QR, where you can get from Q to R using a D switching. And the set Y that we're interested in is just all the non-zero, well, VJ where J is positive. So we really do want entries equal to D. So it's just the vertex set take away V0. Okay. We can apply the previous little counting lemma to give us our functions A and B, which we need, the lower and upper bounds. The upper bound one was easy because that was just SDTD no matter what J is. The lower bound one, we want positive entries which are not greater than D. Well, nothing in the table is greater than D. So if you've got a table sum of S and your biggest entry is at most D, then you've got to have at least table sum divided by D positive entries, and that gives us the value of K that you just stick in here and plug into the lemma. So we can use these in the theorem, and you just apply the switching theorem to get a bound. And it says you've got to be looking at directed paths that start off in your set of interests, so VT1, where T1 is positive. They go down to a sink in the directed graph, and the only sink we've got is V0. So TQ has to equal 0, and that means that Q has to be at least 2. And then you can bound the thing we're interested in. Well, in the theorem, it said you sum along the path all the ones which belong to Y, which is just everything except TQ. And on the bottom, I'm supposed to sum along all the entries in the path, but for an upper bound, I've just left off n of VT1 because I can, because it's greater than or equal to 0, so it doesn't hurt for an upper bound to leave it off. Then you've got q minus 1 summands on the top and bottom, and you can check that that's bounded above by the maximum of the sort of ratio of the successive ones, which is something I never believe. I have to check it each time, but it really is true. And then we just plug in the definition of that function n, which I briefly showed you, which involved a's and b's, and it ends up to look like this. B of mdti on the top, and that's just always sdtd. And on the bottom, there's an a of something, and that just had a of the one corresponding to ti minus 1. We'll have a ti minus 1 out the front, and then some factor, which is this s on d minus 2st all to the dth power. So for the worst case on the denominator, you want the ti minus 1 to be as small as possible, which is going to be tq minus 1, and the worst case of that is when that thing is equal to 1. So that's what I mean by analysing a worst case path, and it's given us this upper bound here, which I'll call psi d. And very quickly, you do a bit of analysis on this, and you find that the first one, psi 4, is already small enough. It fits into our big O that we're after. And then each successive one after that is little o of the previous one. So when you add them all up, in order of magnitude, it's the same order of magnitude as psi 4, which is already small enough for us, and that's it. So that's an application of the switching lemma, which enabled us to prove our key fact number 1. The argument to show that you don't get many 2s or 3s is very similar to this, but it's just a bit more delicate, so I skip it. But it also uses the switching theorem. And I just wanted to finish off for this audience by coming back to sort of practical considerations. We've got this nice formula, but does it really help us if you're a person sitting in an office and you really want to know how big this number is? So is it really competitive with an FPRAS? Well, remember that an FPRAS is supposed to be efficient, and I'm claiming that if you've got a formula and you just have to plug the numbers in, that's pretty efficient. But the problem is this user-defined tolerance. If you really need to know that your relative error is at most epsilon, then we kind of have to say, well, sorry, we just know it's big O of something, which is tending to 0, but we don't have the constants. And I think it would be a complete nightmare to trace back not only our calculations in this paper, but also in the previous work on the 0-1 matrices to find out the constant. So I can't think of anyone in the world who would actually want to do that. So no, it's not really practical if you're very keen to know the tolerance, except maybe it kind of is when you've got the conjecture holding, Canfield and Mackay's conjecture, because there was control over the size of the constant. There's still actually, I didn't show it to you, but there's still a little o1 that tends to come up. Even when we verified the conjecture, there was a little o1, but just assuming that little o1 term was bounded above by 1, which doesn't seem too much of an assumption, it strongly suggests this particular relative error, which you can then plug in and see whether it's smaller than your epsilon or not. But still, we should probably get a student or something to do some simulations, and then more data would tell us whether the conjecture is, well, whether these things really tend to 0 very quickly or not. And that's all I wanted to say.
Any questions? So the range over which you can do this is quite small, away from the regular or semi-regular cases.
If you're away from the semi-regular, so the product of S and T being at most the table sum to the 2/3, it takes a while to sort of unravel that, what it means.
Yeah,
but
I was trying to do that.
Yeah, I'd have to think about it too. I mean, it's something, they can tend to infinity, but there's a big gap between what we can do in the sparse case and what you can achieve in the dense case, a huge yawning gap. But if it's very, very dense, of course, you just, with bipartite graphs, you would use complementation, but what does complementation mean in contingency tables is another matter.
Mark Huber has a recent approach of doing a sort of repeated rejection sampling for estimating sizes. Have you seen that work?
I haven't seen that, no.
Wondering how it compares.
Yeah, sorry.
Okay.
Is that the important sampling approach that you're referring to?
Yes.
Right, well, thanks again, Catherine, and we'll continue with the next talk.